In this video, we're going to look at the estimation cost of our neural model, max frequency, throughput, and power dissipation. So when we want to look at the estimation of our cost, first thing we need to do is to make sure that we have our pin planner assigned, and I have already assigned the pin planner here. So what we need to do now is to compile all the designs. We can just look at the theta to see the cost. So now when we look at the summary report, we can see that we are using total of 19 registers and 19 pins. And this is exactly as how we have designed our neuron. So if you go to the pin planner, you can see this in total here there are 19 pins, and then on the report it says we have total of 19 registers. These are flip-flops, and it is exactly 19 flip-flops that we are using here. So if I can explain, for example, we are using registers. We have instantiate 5 registers. So if we take a look at registers here, so we are using 5 registers, and these 5 registers has using 2 registers on the W, so there are 2 bits, so it is 4 flip-flops, plus we are using 2 registers for X, and those are 3-bit, so it is 6 flip-flops, and the last register that we are using is for the output Y, which is 3-bit. So in total here in the registers we are using 13 flip-flops, and ring counter, in ring counter it is 2-bit ring counter, so we are using 2 flip-flops, and up counter is 4-bit up counter, so it's 4. So in total we are using is 13 plus 2 is 15 plus 4 is 19 flip-flops. That's why it shows here 19 registers. So that is for the cost. Next we can look at the maximum frequency and the longest delay that it have through those flip-flops. So what we can do now, it is to compile the time analyzer, and then we need to launch our time analyzer. And then if we go to report timing, and choose the clock that we have, and from, for example, all signals, choose all signals here, and then OK, and then we can just choose number of report path 10, and then we can look at our worst case path, and then we can see here the worst that we have, it is 2.115 nanosecond, and it is from the register in model 4 to 7 to model 7 Q1. And then this is, if we go to our neural model, model 4, so it is X is from the register X1 to model 7, that is Y. So the answer, which is the second bit from here, it's second bit. So that is the worst case path for delay time. And then we can look at our fmax. So we can go to time analyzer here, and then if you go to slow summary, we can see the fmax that we have 422.83 megahertz. So that is our fmax. So we can take a note of that too. Our fmax, it is 422.83 megahertz. So the next thing that we can do is fix, for example, if you go to the time measurement, you can see that the slack is red. So we can fix this. This is because that we have the estimation, it estimates with large clock. So if you look at the clock here, it choose 1000 megahertz. So we need to change this one. So for example, you can go to clock, and then we can create a new clock, and then we can just write clock here, and then we can choose with a period of 4 nanosecond as our test bench file, and then from 0 to 2, and then we can target the clock here, which is this one. Okay, and then we can run. So the next thing we can do, we can write the SDC file. So here we can make it as a neuron, and then okay, and then we can just read the SD file. Now if we go to report clock, we can see now it have changed to 250 megahertz, that is with a period of 4 nanoseconds. So now if we go back to our timing report and run our time report again, to all signals, okay, and then report, we can see that our slack error is not there. Now we have seen two worst case delay between two flip-flops, which is about 2.11 nanosecond, and the transmitting flip-flop is this one, which is X1, and the receive register, which is Y1. Now let us calculate the throughput, the clock latency between the process. So we're going to calculate it in result per second. So we know that our fmax is this one. So in order to calculate the throughput, first we need to find the period of this on our result. So we know that the period is equal to 1 divided by the frequency, and our frequency is fmax. So this will give us roughly 2.365 nanosecond. And based on this information that we know, the fmax means that the max frequency that we can use on our system. And then we know that our system uses 2 clock, so we can find that the maximum value that we can get through Y per second. So we know that we have 2 clock, so our period then is equal to 2.365 nanosecond times 2, since it takes 2 clocks to compute the result, and then it will give us 4.73 nanosecond. So we know that this is our period now, the maximum period that we can have. So the maximum value that we can print per second, so the frequency is 1 divided by then you can call this T1, or so divided by T1. When we compute this one, you will find that you will get 211.416 megahertz. So in other way, you can say that our system, it can calculate 211 million results per second. So this one was the estimation of the cost, fmax, and throughput. So we have calculated the throughput now here. So in the next video, we will try to estimate the power dissipation on the Quartus.